So we talked a little bit about forces in the last session. We actually applied forces, and we said that a force was some kind of push or pull that could change how an object is moving. Well, based on our experiences in lab and also based on Newton's first law, we can be a little more specific now. We can say, in fact, that forces cause objects to change their velocity. They cause objects to accelerate. Now, the other thing that we need to add here is that if there is more than one force acting on the same object at the same time, we need to find the combined effect of all those forces. And that's where the idea of net force comes in. If there's more than one force acting on an object at the same time, we have to add all those forces together. That's called the net force. That's the cumulative effect of all those forces acting together. If you wanted to write it as an equation, we could write it like this, where there are vector symbols over each F, to remind us that when we add these forces together, we have to add them as vectors. So here's an example of such a situation. We have a box, and there are two forces acting on it at the same time. There's 5 newtons pushing up and to the right, and 10 newtons pushing straight up. If we wanted to know the combined effect of both of these forces on the box, we would have to add them together to get the net force. So remember how we add vectors. We have to draw them one after another, making a chain of vectors. So we could start with the 10 Newton force, and then we could put the 5 Newton one head to tail with it like that. And then if we go from beginning to end, there then is the net force. That red arrow represents the single force that you could substitute for the two forces that are actually there and have exactly the same outcome. Now, for purposes of this class, the important thing is that you can draw this picture, that you can look at it, and you can see that the force, the net force, is going to be up a little bit to the right, and you should also be able to estimate the size of it. If you look at the picture, you can see that the red arrow is definitely bigger than 10, but it's also smaller than 15. In order to get 15, the 5 and the 10 Newton forces would have to be in exactly the same direction. So if you could look at that picture and judge the net force was somewhere between 10 and 15, that would be enough for our purposes. Now, if you actually go through the details of calculating the net force, which requires a little bit of trigonometry, it turns out to be 14 newtons in this case, rounded to the nearest newton. So what we're saying then is that these two forces acting together are equivalent to a single force of about 14 newtons acting up and a little bit to the right. Again, for this course, if you can get the direction and the approximate size, that's enough. You don't have to be able to calculate the exact number. Here's another example. Here we have 3 forces all acting on the same ball. To get the net force, we would add them together. Again, you can chain the vectors together one after another in any order. So we could start with the 50, we could put on the 120, and then we could add the 80. And then to get the net force, again, we just go beginning to end. So there in red is the net force. So you can see the net force is down and to the right. And again, for our purposes, if you can look at that, see that it's down and to the right, and then estimate it from the picture. If you look at it, definitely net force is bigger than 50. Also, very definitely quite a bit less than 120. So if it's somewhere between 50 and 120, probably closer to 50, down and to the right, that's what I want you to be able to do. If you actually do the calculation in detail, it turns out to be about 64 newtons, again rounded to the nearest newton. So those 3 forces acting together would affect the ball in exactly the same way as a single force of 64 newtons pushing down and to the right. You could remove the 3 forces that you started with, replace them with just one single force equivalent to the net force, and you'd have exactly the same outcome. That's the idea of the net force.